like you to y equals 2 to the x. One thing we're going to start to do here today is that we're going to have variables for exponents. It's good times. Y equals 2 to the x. Power of x, yes. No, not really. So you have y equals 2 to the x. I want you to go ahead and hit graph, and you're going to get some funky looking curve. Hopefully everybody's graph kind of looks like that, right? Now let's think about what's going on here. If I'm going to go backwards and look at this as via a table, what's 2 to the 0 power? What's anything to the 0 power? 1. What's 2 to the first power?
2.
What's 2 squared?
4.
2 cubed?
8.
2 to the 4th?
16.
Good.
No.
So you're seeing as each value of x goes up, that's why it's increasing exponentially. If that makes any sense. Now, going the other direction, what would 2 to the negative 1 equal? 1 half. Remember your rules of exponent. It's not happy. 2 to the negative 2. 1/4, and so on and so forth. Do you guys agree? So, as your value of x is getting infinitely smaller and smaller and smaller and smaller, what is the value of y approaching? 0. Very good. Will it ever get to be 0? No. It's one of those things. You can always divide a number in half. You can continually divide it in half, divide it in half, divide by 2 each time. So what happens, what is that called is you're approaching something but you never quite get there? Well, all right, you're approaching it. What is that imaginary line that you're approaching that you don't touch?
What is it called? Asymptote.
Asymptote. You're close. It's an asymptote.
How do you spell that?
How do I spell that? T-H-A-T. How do you spell asymptote? It's A-S-M-Y-tote. I think it's A-S-M-Y-T-O-P-E. I don't know. Come on, this is why I have a degree in math. There was no spelling involved. So what happens here is that you have this horizontal asymptote always going through y equals 0. So here's what's going on. We have these things called exponential growth functions. And each one of these looks like this. Y equals b to the x. But what's really happening here is that you actually have something a little bit fancier. You have this generic form called y equals a times b to the x. This value of a is always your y-intercept. I want you to think about it. This is called a parent function. Now think back to the problem we just had up there. Y equals 2 to the x. I did not have anything written there with the value of a, did I? What's the value of a then that you don't see? 1. Very good. It's 1. It's 1 times 2 to the x. If x is equal to 0, that's where your y-intercept occurs. Remember that? If x is 0, what's 2 to the 0 power? 1. What's 1 times 1? There's your y-intercept. Again, think of it this way. Y equals 3 times 3 to the x. What's 3 to the 0? Again, anything to the 0 power is always 1. So it's never going to be. Okay. So if x here is 0, what's your y-intercept? 3. Again, that's that value of a. Yes, sir?
What is 0 to the 0 power?
1.
No matter what.
Mm-hmm.
That's
And I don't know.
contradictory.
Crazy.
I think that's
I don't know. It's the one that doesn't quite work.
That doesn't work.
Theoretically, it's 1. Realistically, it's not possible. Realistically, thank you. Made up that word. You like that? For example, if I look at this simplistic function, if I look at this simplistic idea of y equals 1/2 times 3 to the x, when I go to graph these things, bless you. When I go to graph these things, it's in the form of y equals a times b to the x power. So, bless you. Again, since there's nothing tacked along with this, it's just y equals ab to the x. I know I have a horizontal asymptote. At y equals 0. And I also know that my my y-intercept is going to curve where? At 1/2. So I know the two things happen. The horizontal asymptote at y equals 0. I know that this is my value of a. So I have a y-intercept at that value of a. And now I have to figure out some other point to plot. What's 3 to the first power? What's 3 times 1/2? 3 halves. So that's 1.5. Do I have 2 points?
Yes, you do.
I know that all of these are going to have the same style curve to it. It's going that direction. And you just graphed an exponential function. Basically, when you're graphing these types of problems, ladies and gentlemen, you're going to plot your y-intercept and any other point. Take the curve. And again, when you look at these things, your values of x, it's totally up to you what you want to use. Could I have used 2 and done 3 squared and then multiply it by 1/2?
Yeah.
Got the same. I would have had it. That point would have also lied on that same curve. All I need to be able to do is pick a point, plot it, and remember to put my y-asymptote in, or my horizontal asymptote in. Okay. But also, going with every other graph that we've ever done, we had a parent function, and then we had the shift. And when we shifted things, what did we write it with? You shift things horizontally and shift things vertically. What do we use? H's and K's. So along with these things, you will also see shift. Y equals a times b to the x minus h plus k. This is your shift. And what does the h stand for again?
Horizontal.
It's your horizontal shift. And your k is?
Vertical.
And then when you shift things vertically, y equals that k value will become your new horizontal asymptote. Okay. One thing I did forget to mention is that whenever you see these written out, they will always split that up and put the like 2 times 3. Okay? They will always, if there's an a value that's not equal to 1, they will always write it as something times that. It's not going to be something you have to try to figure out. It's going to be very blatant what it is. If you don't see something there, if it's just 3 to the x minus 1, what's your value of a? 1. Does that make sense?
Yeah.
So let's look at what this means. If I take that example, I have 2 times 3 to the x minus 1 plus 4. And I'm going to graph that. Oh, I forgot to give you this. Take a couple of sheets, one for now and one for later.
Oh, it's big statement.
Yeah, a couple of them. All right. So let's take a look at this one then. Now, if you guys remember when we first started working with A, H's, and K's, remember one of the first things that we always did with that is we always listed out what each one of those values was equal to? I'd like to start doing that again here, just because it'll help us get accustomed to everything. So in this example here, what's your value of A? 2. What's H? 1. And what's K? 4. Remember, those same rules apply when you have the opposite of H and then the same value of K, okay? So that gives me my values of A, H, and K. When I go to graph this, if you remember when we graphed, I think it was absolute value functions, we had a parent function, then we shifted it. Remember how we did the thing with a dotted line, then we shifted it left and right, up and down? We do the same thing with these as well. What we're going to do here is we're going to graph the parent function first. And the parent function of this is going to be y equals 2 times 3 to the x. That's going to be my parent function. I don't worry about the h's and the k's. When I go to graph that, what's my y-intercept? 2. My y-intercept here is going to be at 2. And now I just got to figure out some other easy point to work with. What's 3 to the first power? 3. And what's 3 times 2? 6. So if x is 1, y would be 6. In the parent function, where is your horizontal asymptote going to lie? At 0, very good. And do you guys remember when we did, you can just leave a pile back down here later. When we graphed the parent function, was it a solid or a dotted line? Dotted. Question?
So how do you find
The asymptote for the parent function, it's always going to be at y equals 0. And the reason that is because there's nothing tacked on back here.
But
All right.
then it's different for the shift.
It's different than shift because now what's my shift at? It goes up 4, so where's my new asymptote going to be at? At 4. It will always, always, always be the k value. All right. So here, well, did you guys tell me if it was solid or dotted? Dotted, good. So you just. And what do you think I have to do to each of those points to graph the parent function now? Move them to the right 1 and up 4. Right 1, up 4. Right 1, up 4. And I have a new asymptote now at, and now I just make it a solid line. And that's all there is to this. Graphing exponential growth, and then tomorrow when we graph exponential decay, follows the same basic principle. You're always going to graph that parent function, that ab to the x, and then shift your points to your horizontal or vertical shift. You do not need to worry about picking weird, crazy points to make that work. All you need is a pair of points, and you're good from there. Okay? Does that make sense? Yep. Or it would move down if it was a negative value. Okay. All right. So let's take a look at some. Another example. It's basically the same problem we just did. All right, try this one. Take a second. Give it a shot. You go to start this. What is your parent y equals a times b to the x going to look like? What is that value? What's your value of a?
1.
I'm going to graph that first. Remember, if there's nothing in front of the whatever is being raised to the exponent, it's always a 1. So this is going to be my parent function. When I go to graph that, I know that the value is 1, so that's going to be my y-intercept. I know that my original asymptote is going to go through here. Then all I have to do is pick another value. So I pick 1. 2 to the 1 is? 2 times 1 is? So that 1, it's 2. And it's going to look like this. To that, I have to move it. My A was 1. H is 3. And K is 1. I have to move it to the right. How many? 3. And how many up? 1. There you go. Move to the right. new asymptote. Whee! And there's my new curve.
Hey, I got something to say.
Always put the parent function in first, yes. Just like always have. One of the things you guys will see throughout all of these graphs that we do second semester, there will always be a parent function and a shifted function. If any graph that you have to do has a shift to it, your first rule will to always, 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 always graph the parent function, and then from there, shift your value of points. You're going to find out that no matter what we use, it's the same basic principle. Exponential growth, decay, the E values, and we graph logarithms later on next week as well. When we get to the trig values, they're big, they're heavy, they're wood. Thank you. You got that.
You said that last time. What did you say? What's log? Logarithm.
The second part of this section, not only is just about graphing, is we talk about what's called an exponential growth model. These things are stuff that you will see in your science classes, quite often actually. Are any of you guys taking business anytime soon? You'll see this with compounding interest, things of that nature, depreciation. You see these compounding exponential growth or exponential decay. Well, the first one we're going to talk about is called an exponential growth model. These exponential growth models all start out the same, where this value of A is your initial amount. R is always this percent, but it's written as a decimal. And T is usually time. It's usually in years. I don't think most of our things change via years. Okay? The junk that's within the parentheses is always going to be called your growth factor. See it? This 1 plus R. So what happens here is you'll see this a lot when they're talking about population growth. If, let's say, the town of DeKalb started out with a population of, let's say the population was 25,000 people in 1990.
Okay, sounds good.
Okay. And let's say the population increased. Done. If you really want her shoes, you can go to the store and buy them. Or go get a hacksaw. Just joking. Then we can call you Stumpy. I'm sorry, that was bad. Anyway, let's say that your percentage of annual growth rate was at 4%. What you do with these values here in order to figure out what the model will look like given those specific parameters is that you now know what your initial amount was. You know when where your starting point of your time in years was. For example, if I'm saying the population was 25,000 in 1990, that's my starting point of 0 for time. 1990 to 2000, T would equal 10, because it's time since the first data given to you. Does that make sense? That's usually tough for people to understand. All right. 1990 to the year 2000. Yeah. All right. 4%. How do you write 4% as a decimal? 0.04. Good. So let's see here. Let's take this basic information and let's see if we can come up with what this would look like via a model using that. So our growth one. What's your A value in this case?
25.
Our R is going to be 0.04. And I'm just going to leave it in terms of T for right now. So when I write this out, it would be Y equals 25,000, 1.04 to the T value. Yeah, because now what happens is that you're able to get this baseline. And when I'm talking about growth here, it's always the same idea. Your growth rate, that growth rate factor, this jump that's in the parentheses, will always be larger than 1 because it's 1 plus some percentage. So let's say I wanted to kind of get an idea of what was the population in 2013. So what's your value of T? 23. So exactly, like you were saying, you go right to your calculator. Now what's nice about these population growth style models is that you can type them into your calculator exactly the way that you write them out. So we start out with, once I clear this up, 25,000 parentheses 1.04 to the 23rd and enter. So there's 61,617 people. Now, if they're talking about people, you're always going to round to the nearest whole person. We do not have half of people walking around. Okay. Oh, we do have Stimpy, you're right, but she's still a person, a whole person in our hearts.
Yeah.
Well, that's true. So I would say there'd be, in 2013, if this was the correct model, there'd be 61,618 people. Does that make sense? But we just want to run them. Okay? Does that make sense? So the other thing that you'll see with these growth problems is that it might give you a model. For example, it gives you a model that looks like this. Winnemucca, Nevada? Yeah, it's just south of Vegas. If your population, the population model is 6191 times 1.04 to the T, what would be in the population in 1990? What is the percentage of population growth? 0.04% is not correct. What is the percentage? It's 4%.
Oh, I'm sorry.
Remember, they're going to write it as a decimal. You have to convert it back to the regular percentage. So if it's 1.04, that means it was a 4% growth. Tomorrow when we talk about decay, it's going to be 1 minus the rate. So if it was 0.96, it was a 4% decrease or depreciation in value. All right. In this case here, what was your initial population? 6191. Okay. This is the kind of stuff we're looking at with these growth models. There's two different types of things we're looking at today as far as growth models are concerned. We're talking about this basic population style, and then we're going to talk about compounding interest. The compounding interest ones deal with money. Growth models generally don't. That's a big idea of how you're able to decide what type of model you're working with. When we're talking about compounding interest, again, each one of these things stand for something, and I'll go over all of it with you. Plus your rate over N. What's going on here is that when you open a bank account, the amount of money you hand over to the banker is called your principal. It's what you're starting with. Okay? That's what they call the value of P. P is the principal amount. And it's how much you start with. What do you think R stands for again?
Rate.
Yeah, R is your rate. It's a percent, always as a decimal. Oops. N, the number of times it compounds. And I'll explain this in a second. For example, if it says something compounds annually, how many times does it compound? Once every year. Semi-annually. Twice a year. Quarterly. 4 times a year. Monthly. Daily. 65, okay. So again, you guys get the basic idea of what the N value stands for here. It's the number of times something's going to be compounded. It's not going to say it compounds twice a year. No, they say semi-annual. Why? I don't know. They just sound fancier that way. R, again, is always going to be your percentage written as a decimal. And then the T is going to be however many years you're doing this for. Okay?
What about A?
A is the amount. How did I write this up? Amount when finished. Yeah, like your finished amount, your total amount.
Final amount?
Final amount, total amount, yeah. So if you go to the bank and you're going to put the bank in, you're going to put $500 in a savings account. I'll write this up in a second. If you go to the bank and you have $500, you want to start a savings account. The bank savings account might give you 2.5%. I don't even think it's that much. Maybe 1.5%. We'll just say it's 2% for fun. Okay. So let's say we go to the bank with $500, and you're going to deposit it at 2.5%, and it's going to compound quarterly. And you're going to leave it in there for 25 years. You're going to save your money for 25 years. So when it's done, then you go out and buy a car. So now you know a whole bunch of stuff. You're trying to solve for what it's going to equal when you're done. You're going to use the growth model of your principal is 1 plus your rate divided by the number of times it compounds, all raised to the number of times it compounds times number of years. Now again, what's really nice about your calculators is that you can type it in exactly like that with the alpha y equals to create a fraction and substitute all your values right in. It works out real nice. So let's see. Let me move this over a little bit. What's my value of P? What's my principal? 500, so I start with that, 500. Open a parentheses, 1 plus, I'm going to create a fraction again. Remember, alpha y equals. What's my rate if it was 2.5%? 0.025 over, if it's compounding quarterly, what's the value of n? 4. Good. Now you know, hit the right button to get out of the fraction. Close your parentheses, and then it's going to be raised to the, 4 times 25. We could probably just write that out, correct? 100. And this is how much money you'll have after 25 years. $932.30.
That's cheap car.
Very cheap car. What's that? Louder, you mumble.
Is that how years?
That's 25.
10. It's 25 years because it's compounding quarterly. So then,
Oh,
okay.
That makes sense.
All right. So what's happening here is that your savings account's not going to help you make a lot of money. Now, the other question, I brought this up third hour. Obviously, when you're dealing with this stuff, you're dealing with money. They only round it to the nearest 100, 2 decimal places, correct? What do they do with all the money, all the decimals tacked on at the end? Did you ever see Office Space?
Yes.
Nobody? I know you,
I-
the only couple
I just
people.
said yes.
I highly recommend it. Seriously, it's inappropriate for school, but it is a very, very funny movie. What their scam was all those decimals after the hundredths place to scam out of banks. Within a matter of hours, they had a couple of $100,000, like, oh no, and they shut it down right away. Because what do you do with all those parts of cents? That's what happens. It just gets truncated out. So,
What do they do to make money?
Well, they had, instead of rounding it off, they had it go into a separate bank.
yeah,
account.
instead of rounding it to 30 cents, or instead of going up to 31 cents or going to 30 cents, they take that 7 thousandths of a cent and just have it thrown into a bank account, and those money just all of a sudden just compounded up real fast.
And then, but they accidentally like made it round off like whole.
Yeah, I recommend the movie. It's very, very funny. It's well written. It's got to be, what was that, 92, 94 maybe? It's got to be pushing 20 years, 15, 20 years old. It's a great movie. You guys would love it. Anyway, so what happens here when you substitute all this stuff in, you'll see that we're going to have equations that you guys should be solving for, not always for the amount after everything. You might be solving for the number of years it was in there. You might be solving for the percentage rate. So you will have multiple step equations here or there. These growth rate compound interest problems should not be horribly scary bad to work with. All right? Try another one? Let's try one. This one's boring. Oh, well, we'll just do that one. All right, we'll go back to the $1,000. You're depositing $1,000 into an account that pays 8% annual interest. Find the balance after 1 year if it's compounded with the following frequencies. You guys do the annual. You guys do quarterly. You guys do daily. And we'll see the big differences between them all. So if you're doing daily, what's your value of n?
365.
If you're quarterly, if you're annual, 1. Good. Tomorrow we'll talk about depreciation. I know a lot of you guys just got your driver's license because you guys have been talking a lot about that, I hear. Don't buy a new car. You will see that depreciates very, very, very rapidly.
Oh, is that when you buy it and then you drive out?
Mhm. Oh yeah.
Instantly.
I'll explain to you guys what that means and how that works. Depending upon the car.
Would 8% be R?
8% would be R, yeah. And what do you change that to?
22, right?
All right.
How does that help in going into?
Annual, how much money did you have? How much total?
$1,080.
Any change?
80 bucks.
Nope. All right, how much money did you guys have?
I got one.
Oh, wow. 1,000.
There's not that much of a difference when it doesn't start to get, until your time really gets stretched out, is when you'll see more of a higher rate of return. Okay? Let me give you a couple you should try tonight. Now, in these problems here, I gave you, I think 6 of them are graphing. 1 or 2 of them are just the a, b to the x. The other ones are your shift. If you're graphing ones with the shift, it means you have to have the parent as well as the shift. The last bunch are all these principal interest style problems. Exponential growth models. In those numbers 43 through 54, it says do all of them except the ones that say graph. Bless you. There's a couple of problems in those sets that says graph the function. There's no point to graphing some of these growth model functions because you're never going to be able to see them on the screen of your calculator, and you don't really need to see the graph in order to answer the questions. So don't worry about those graphs. And then the last group are basically all interest problems. They're very, very, very straightforward. All right? And we'll go with DK tomorrow.